Hello, my name is Alejandro Datas, and I will talk about latent heat thermophotovoltaic batteries. A latent heat thermophotovoltaic battery stores the electricity coming from variable renewable energy sources like wind or solar in the form of latent heat at very high temperatures, and when needed, convert it back to electricity using thermophotovoltaics by taking advantage of the thermal radiation that is emitted by these high temperature materials. As any other energy storage systems, there are three key performing indicators. One is related to the energy storage capacity of the system, which is the cost per energy capacity in euro per kilowatt hour, and the other two are related to the energy conversion processes in the system. In this case, the most important one is the conversion of heat into electricity by thermophotovoltaics, and the parameters are the cost per power in euro per kilowatt and the conversion efficiency. The cost per energy capacity depends on the cost and the energy density of the material that is used to store the heat. In this figure, I show the volumetric cost in euro per liter and the volumetric energy density in kilowatt hour per liter of different materials that includes phase change materials that store energy in the form of latent heat and other sensible heat options. In this figure, the straight lines represents the cost per energy capacity in euro per kilowatt hour. And we can see that the lowest cost per energy capacity are obtained for low volumetric cost and high energy densities. Among the several options that we have, the lowest cost are in the range of 1 to 10 euro per kilowatt hour. And this is 2 orders of magnitude lower than the cost of lithium-ion batteries that are over 100 euro per kilowatt hour. From the low-cost options, we find, for instance, solar salts that are used in concentrated solar power plants. And the problem with these salts are that they have very low energy density, and therefore they require very large container that represents a large portion of the total cost of the systems. An alternative is to use materials with higher energy density. For instance, this is the case of silicon that provides energy density over 1 kilowatt hour per liter that enables the use of much smaller containers and therefore enables a lower cost per energy capacities. Besides, silicon has a very high melting temperature that matches very well with the application of thermophotovoltaic energy conversion. Regarding thermophotovoltaics, as I said before, the two key parameters are the conversion efficiency and the cost per power in euro per kilowatt. The conversion efficiency is represented here for the case of indium gallium arsenide cells with a back surface reflector having different reflector reflectivities from 90 to 99%. We can see that for the temperature range of interest for the application of silicon as phase change material, we can have efficiencies in the range of 30 to 40%, which matches very well with experimental results that have been obtained very recently by several teams at this temperature range. Regarding the cost per power, we see that this cost depends, of course, on the temperature of the meter, but also on the cost per unit of area of the cell. And here I show three assumptions for this cost from 2 euro to 0.5 euro per square centimeters. And we also can see that for this temperature range of interest, we could expect costs between 200 and 1,000 euro per kilowatt. So these three are the three key performing indicators of a latent heat thermophotovoltaic battery. So we can plot these three key performing indicators in a figure of this kind, where I show the cost per power, the cost per energy, and the conversion efficiency, and compare with other energy storage technologies like lithium-ion batteries that for stationary applications have cost per energy capacity of 300 euro per kilowatt hour, cost per power of 380 euro per kilowatt, and conversion efficiencies over 95%. If we plot here the case of latent heat thermophotovoltaic batteries, we see that the main advantage is the lower cost per energy capacity, but there is no clear advantage regarding the cost per power, and the conversion efficiency will be definitively lower than in the case of lithium-ion batteries. This is the reason why this kind of energy storage system is very well indicated for long-duration storage applications, where there is a very high energy-to-power ratio, and the conversion efficiency is not that important. However, we could also use latent heat thermophotovoltaic batteries in short duration storage applications if we make use of the heat that is produced from the cooling of the thermophotovoltaic cells. In this cogeneration approach, we will have a higher overall conversion efficiency and a lower cost per power, as in this case we have two kinds of output powers. Now we are going to compare these two technologies in a particular application where we have a fully electrified building with a solar PV installation to satisfy all the energy demands that include domestic hot water and space heating, cooling, and electricity demand. Therefore, we need an energy storage system, in this case the lithium-ion battery, some hot water storage to provide heating needs, and a heat pump to provide the cooling. If we substitute the lithium-ion battery by the latent heat thermophotovoltaic battery, we can now provide the heating needs from the cooling of the cell or directly from the high-temperature heat store. The thermophotovoltaic generator will provide electricity to supply the electricity demand and the heat pump for cooling. Obviously, in this case, we will have also some heat losses from the high-temperature heat store. Now I'm going to show the specific cost of the two solutions in euro per kilowatt hour that represents the total cost divided by the total energy demand. And the total cost includes not only the investment cost, but also the operational cost that include the cost of the electricity that is needed as a backup. Here in the blue region, I represent the results for the lithium-ion battery, assuming today's cost per energy capacity of 300 euro per kilowatt hour and the future projections of 150 euro per kilowatt hour. Now I'm going to superimpose in this figure the case of latent heat thermophotovoltaic batteries under the worst case scenario for the cost per power of 1000 euro per kilowatt. If we also assume the worst case scenario for the cost per energy capacity of 30 euro per kilowatt hour, we see that latent heat thermophotovoltaic batteries do not bring a clear advantage with respect to lithium-ion, even at very high thermophotovoltaic conversion efficiencies. So let's make some assumptions for the causal reaction of the energy capacity. If we could reach cost per energies of only 5 euro per kilowatt hour, which is still higher than the cost of the material that is used to store this energy at these high temperatures, we could beat lithium-ion batteries with conversion efficiencies just over 20%. If we make further improvements in the cost, in this case related to the power part of 300 euro per kilowatt, we see that we could beat lithium-ion batteries even in the worst case scenario for the cost per energy capacity of 30 euro per kilowatt hour, having efficiencies only above 20%. It is also important to remark that having efficiencies over 20 or 30% does not bring a clear advantage, and this is because the heat that is delivered from the cooling of the cells is put in good use for delivering the heating demands. Now I'm going to show some experimental efforts to develop a lab-scale prototype that has been conducted in the frame of the European project Amadeus. Here you can see some pictures of the system, including the full chamber that has been manufactured by Ion Back Process, an Italian company, and enables to create either vacuum or inert atmosphere in their entire system. Here's a detailed picture of the crucible that is made of carbon and is very well isolated from the environment by using carbon-based thermal insulation materials. Finally, you have here the thermophotovoltaic cell that is facing the bottom part of the crucible and is made of a gallium antimonide from GS crystals. Here you can see a picture of the system in operation, where you see the crucible at over 1000 degrees Celsius and the thermophotovoltaic cell at temperatures lower than 40 degrees Celsius. Just as an example, here are the IV curves that have been recorded for this cell when the crucible temperatures go from 700 to 1020 degrees Celsius. We have conducted preliminary experiments using copper as a phase change material. Here you can see the pictures before and after the experiments. And on the bottom you see a graph that shows the temperature of the bottom part of the crucible as a function of time for two cases where we have an empty crucible and a crucible that is filled with 3 kilograms of copper. So we see here that the phase change occurs in a narrow temperature range that is slightly lower than the melting point of copper just because the temperature is measured in the crucible but not directly in the copper. So if we look at the phase change process, we see that the temperature is kept more or less constant, and this is mostly because of the high thermal conductivity of copper. During the solidification, we see that there are two fronts, one from above and one from below, and the one from above is related to the very high amount of losses that exist in this lab scale prototype. Here I saw a possible future large-scale prototype of 50 kilowatt-hour of energy capacity, where the PCM is contained in a cylindrical crucible, where there is an optical cavity where you can introduce the thermophotovoltaic generator. This system has been described in this publication and has the advantage that can be easily scaled up to larger energy capacities. And here I show the case of 500 kilowatt-hour system. And the advantage of making large systems is that we can increase the volume to surface ratio, and therefore we can reduce the amount of heat losses of the system. In summary, latent heat thermophotovoltaic batteries could beat lithium-ion batteries not only in long-duration storage applications, but also in short-duration applications if we make use of the heat that is produced during the cooling of the TPV cells, and therefore we use the storage system in a cogeneration approach. However, we need to meet some key performing indicators, such as a TPV conversion efficiency over 20 or 30%. The cost per energy should be lower than 10 euro per kilowatt hour, and the cost per power should be below 500 euro per kilowatt. Thank you very much. I'm happy to take your questions.